Hello everyone, it's December 11th. Alright, let's do this. Nth magical number. Finally we got back to the hard one. Oh, let's see how we can do today. Yep, new question. Nice. A positive integer is magical if it is divisible by either a or b. Given a three integers n, a, b, return the nth magical number. Return this. If it is divisible by either a or b, so if it's 2 and 3, the first one is 2. The fourth one, okay. So it's going to be 2. Next one is what, 4? Next one is 6. No. 3. 2, 3, 4, 6. I see. Oof. So basically we need to find a list of values, right, that is divisible by each. So we're going to have two lists. Let's say one list is for 2, the other list is 3, right? And then it's 1, 2, 3 all the way down. So 1 times, so all times 2, 3, 4, 6, 6, 9, right? And then what's the next? 8, 12, and going on. So all we need to do is merge these two lists. Okay, so merge these two lists. But this, depending on how big n is, alright, we can definitely do it this way. It's a merging, right? It's merging two lists, and we want to, we can merge the two lists. That's definitely how it is supposed to be, but the problem is n is 10 to the 9th. Alright, if we merge two lists, and then take ON, which apparently is not how it should be. If we want it to be, well, if you go like n is 10 to the 9th, we're looking for O log n at least to make this thing work. Okay, ON is not going to work, so might as well not think about it. 10 to the 9th is like what, 1 billion. And plus, the mod is fine. Mod is actually fine. I don't worry about a mod too much. Do we have any clue? I don't know. Any clue? Well, what we do have is towards 10 to the 9th, we have all the values, right? We have all the values. I feel like it, I don't know. Let's try. So what we have is 2, 4, 6, 8, 10, 3, 6, 9, 12, 15, right? That's n equal 5. That's not actually n equal 5. That would just do 5 for each one of them. And if we merge these two, what we get is 2, 3, 4, 6, 8, 9, 10, 12, and 15. How do we obtain this? want to find the nth value, right? So these two, if we go n on both, then we definitely have 2n values, right? So we have 2n least. If it's 2n, well, it could be duplicates, but duplicates. Oh my god. That is another concern. But if we go n at least, that should be fine, right? Can we binary search this? How? How are we supposed to binary search this? Okay, how about n equals 6 given 2, 3. That should give us answers 9. N equals 6. And this one we get 5. We can get 6. That's fine. We can get 6. Oh, we can get 6. That's okay. And then what? And then we say, we try to find 6 on each. That doesn't make any sense. Well, if n equals 6, right? 6th, we can say, we take a guess. The first guess will be the value. Okay, I take a first guess, it's going to be the small value times n. So 8 times n, let's say my guess is 12. Okay, my current guess is 12. So we throw 12 in and see which position it is. So we throw 12 in, right? And the first we get, the position is going to be the 6th, right? And the second one, 12, the position is 1, 2, 3, 4. It's the fourth one, right? It's the fourth one. So overall, 12 is not the 10th, right? 1, 2, 3, 4, 5, 6, 7, 8. 12 is number 8. So we need to know how much overlap there are. Okay, we're talking about overlap now. How are we going to handle overlap? What is overlap? Overlap is the value that both of them. Well, if 2 and 3, they're co-prime, so the overlap would be the 1 divided by 6. So we go 6, right? 12, 18, and blah, blah, blah. So I'm 12. Okay, so we look at the overlap. 12 is divisible by overlap. It's fine. Let's see. So we have 12. So 12 divided by 6 is equal to 2. So I have 2 overlap, right? So 12 divided by 2 is 6, which means I'm the 6th on the 2 sides. Divided by 3 is 4, right? So overall, it's the 10 side. Then divided by 6 is 2. So 12 is the 8th one. And we want a 6, we want something smaller than 12, right? So the next thing we look for is the smallest is 2, so 2 to 12, so we're going to find the middle, right? So 2 to 12, that's 7. Right, that's 7, but 7 doesn't exist for either 2 or 3. So what do? Well, if we got 7, we can get a value. We're going to get a value that can be divisible by both. No, not by both, either one, right? By either one. So it needs to be a value that's divisible by either 2 or 3. So when we get 7, we can divide it by 2 and multiply by 2, which will give me 6. And divide it by 3, multiply by 3, which will also give me 6. So looking for 6. Okay? So 6 on the top is the third one, right? On the bottom is the second one. And on the 6 is 1. So it's 3 plus 2 minus 1. So 6 is number 4. Which is correct. 6 number 4. So that's too small. We want number 6. So we're going to go higher. Right? So we go higher, so it's going to be between 6 and 12, right? So 6 and 12, that's 18, that's 9. We're going to get 9, right? So 9 divided by 2, so we're going to get 8 or 9 itself. So we're going to try 8 first. So we're going to try 8 on the top. 8 is the fourth one, right? On the bottom, 8 divided by 3 is 2. Right, 8 divided by 3 is 2 point something. So there are 2 that's smaller than it. So 4 plus 2. And 8 divided by 6 is 1, so minus 1. So 8 is the 7th. 1, 2, 3, 4. 1, 2, 3. No, not 7th. 5th. 1, 2, 3, 4, 5. That's correct. All right. So 8 is no good. We need 8 is no good. So 8 is too small. So we need something bigger for 8. So something bigger for 8. So the low we're gonna go to 8. All right, so it'll be 8 to 12. And now we can also do 9. And 9, definitely we will find out 9 is correct. Because 9 is 4 plus 3 minus 1. And then boom, we found it. Okay, to summarize, this method is we will obtain the value times n, right? We'll obtain the value and that's like the upper bound, right? We'll obtain the upper bound. But the question is, we have to return modulo 10 to the 9. So while we're doing this, can we do modulo along the way? What should I say? We can pick the nth, right? So the start value is going to be n times small, right? So we know that's n. And then we can get, on the other side, we can compute how much the other side is, and we can compute the doubling. Okay, that we want to solve the one part is if A and B are co-prime. What if A and B are not co-prime? Well, we need to find the overlap, right? If they're not co-prime, like the last case, A is 6, B is 4. So A is 2 times 3, B is 2 times 2. Right? Therefore, therefore, 6 and 4. What are their overlap? They're not 24, right? It's what? It's 2 times 3 times 2. All right, so what is this then? This is the least common multiplier, right? Yeah, that is the thing, least common multiplier. Which is 12. So anything that's a multiplier of 12 can be divided by both 6 and 4. Yeah, so that is the, okay, so can we find that? For something can be divisible by both A and B, right? By both A and B. So we find the smallest one that can divide both A and B. We find the smallest one that can divide both, and all the other ones must be a multiple of this. Yeah. So it's a smallest common multiple. We have a thing for this, right? LCM, smallest common multiple. Least common multiple, okay, least common multiple. Gotta be a formula for this. 12 is the least common multiple, exactly. What are the... Yeah, see, they're all divisible by 12. 1, 2, 3, 4, 5, 6, yeah. Calculation. GCB. Yeah. A times B divided by GCDAB. Okay. So we obtained this, right? So now we have 3 values. Now we're talking. Yeah, I think we can go for it. So basically, we're gonna given an n. We can actually try n. All right. Well, it's gonna be n times a. Yeah, that's how we're gonna try. So we're gonna go n times a, and if n times a is too big, then we have to shrink it no matter what. But if n times a is too small, then we can try n times b. And we'll make sure a is smaller than b. All right, we'll just swap them, and we obtain the common. So now we're talking about from 1 to n, right? From 1 to n. And all we need to do is n times a divided by b, right? N times a divided by b. This one we can get the b, and n times a divided by the LCM of a and b. And then we see what are we looking at? So we see if that value is the n we want, right? Is the n we want. It's too big, then n has to get smaller because n times b would definitely be larger, right? So it has to be smaller. Let's try this. Let's try this. So we start by trying n equals not n. We start by trying the we have left is 1, right? We try the right equals 3. And the first value we try is 12. So A, we set A is 4, B is 12. LCM is, B is 6, LCM is 12, right? So we try, left is 1, right is 3. So the first value we try is, so right is 3. So the first value we try, now right is now 3. So the first value we try, so right is going to be infinite. We can do better. I want the first medium is going to be 3, so it's going to be 6, right? 6. When I start, the right is going to be 2n. So the first medium we try is going to be 3, right? So if it's 3, so target value becomes 12, and then we're going to count 12 on the 6. So once we're 12, so we're going to say, we're going to call it MA and MB. MB will equal to 2, right? And M duplicate, so MD will equal to 1. So the total is going to be 3 plus 2 minus 1. That's 4. So 12 is the fourth one, right? So that's too big. Therefore, we're going to try again. So the next one we try, the right is going to be 3, right? So the next one, right is going to be 3. Well, are we going to be 3 or are we going to be 2? Well, we're going to be MA minus 1 because MA is 3 is too big. So next round, R is going to be 2, right? R is 2. So when R is 2, MA is 1, right? MA is 1, so we're looking at target to become 4, right? So 4, MA is 1, MB is 0, as everything is 0. So now what we have is 1. That's too small. So we go back up. 2. L equals 2. Now they're equal, so 2. So MA is 2. So target becomes 8. Right? MB is 1. Right? MB is 1. And MD is 0. So overall, that's 3. That's exactly what we want. And if it's still, if it's too small, we should try the other one. Oh, okay. Okay, that's actually not right. We have to try both. If it's too big, then we immediately go for the next round. If it's too small, then we're going to try the bigger one. Let's write it up. Let's see if this one works. I mean, it feels like, right? It feels like it's okay, but we'll see. See how it goes. Hopefully this solution works. So first of all, we need LCM. Python, how do we get GCD? Python, GCD, is it math? I think so. If not, we have to write it ourselves. Math.gcd, yeah, it does. Alright, so we import math. And we say LCM equals A times B divided by GCDAB, right? Math.gcd. Okay, so now we have 3. And we say left, right equals 1 and 2 times n. Right, that's how I start with. So while left is, I like to do smaller than r, right? And then mid is left plus right divided by 2. That's all fine. And then we're going to try to find MB. Actually, we're going to say it's MA. MB will equal to MA times, all right, MA times A divided by B. MD equals to MA times A divided by LCM, all right? And we say if MA plus MB minus MD is larger, but if it's equal to n, right, then we're going to return MA times A mod, right? Get mod equals 10, 9 plus 7. We're going to do this. If MA plus MB minus MD is larger than, so if that's too large, we don't have to try B again. We just immediately we say R. The right shrinks down, but the left, wait, is it right shrinks down? Or the left plus? Damn, I forgot. The left shrinks down? Or, well, because of the bias, right? Plus a bias, so we want the left plus. So R stay where the way they are. So right, stay where it is. We're gonna go R on the left, go up. Okay, so R will equal to what? MA. Right, because it's too big, so we want to shrink down. And continue. All right, now this case is this one's smaller. If it's smaller, then we're gonna try MB, right, equals no, we're gonna try MB equals MA, and then MA will equals to MB times B. Oh, we have to also swap these two, right? And then AB equals min AB and max AB, right? So now MA equals this divided by A, and MD equals MB times B divided by LCM. So we're doing the same thing, exact same thing, right? If this, if we swap it, if E equals N, we return MB, right, times B mod. If, oh, what if it's like in between? One is smaller, one is larger. That's a good thought. What if we try this And then we get, so what? So it will be, this is too small, all right? We do MA times A. We say that is too small. It's smaller than N, okay? But now we do, so first of all, if it's smaller than N, all right? If it's smaller than N, then that means, so like this is smaller, right? If we try, this is smaller. Actually, it'll be easier. Let's just do it one more time. So this is too small, and this is too small as well. So if both are too small, that means L needs to be MB plus 1. All right, too small. So we do this, and now we continue. Last case, it's small for this, but big for this. How do we handle that situation? The first one is too small, but if we do the second, that will be too big, right? So in that case, it's too small if we do this, but it's too big if we do this. What does that mean? That means the actual value, yeah, like it should be this. L needs to be get bigger, right? Because the current MB, right, the current count, if we count based on the smaller value, it's too small. If we count on the larger value, it's too large. So the actual value must be, right, it must be larger than what we have right now, because we're going to count on the small. Therefore, I am pretty sure this one doesn't have to count. So we're going to just check the big one. If the big one is not working, right, whether it's too big or too small, because it's too small for the top, right? If it's too small for the top, then we always can go bigger, but we just need to do one more round of check. So that's basically one more round of check. Yes, we just do one more round of check, but if it's not, we're just always going to do this. And we're going to keep going, keep going, keep going. I would hope that one of these will hit. What if they don't hit? Like this one does not hit, this one does not hit. If they do not hit, I mean, they gotta hit, right? They gotta hit. Because it will happen. Or unless, well, L will be equal to. So what if we just do equal to? If we do equal to, then both change, right? If both change, then I think we can guarantee that these conditions will hit. Otherwise, I have to write something down here, like L equal to R. All right, when L equal to R, then we can, but I don't know if it's this one or this one. So yeah, let's try this. Oh, I have a bunch of test cases. I don't even need, because I have test case, right? I have 2, 3, A, B is 2, 3, right? And N, we can go from 1. 1 is going to be 2, right? I have all the way 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have all the way to 9. Right, so we have, oh my dear Lord, that's not dot. Alright, so we're going to say this is going to be 2, 3, 4, 5, 6, 7, 8, 9. Alright, and then on this side, that's 2, that's 3, 4, 6, 8, 9, 10, 12, Oh, I just realized that's actually, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is not 15. Come on, 9 is 14. 10 is 15. All right, have to keep going. 14. 14 in between, and then 15. So that's that, and we can also do another one. Let's call it 4 and 6, right? 4 and 6. Well, 4 and 6. Let's basically use this. I will have the 2 and 4. Number 3, all right? 3 shall be 8, and 2 and 4. Number 5, 2 and 4 shall be 10. All right, so these are all the test cases. NAB, nth magical number, A and B, NAB. All right, let's see. Oh, we passed everything. Oh, wow. I am not expecting this. All right, we're going to test something else. Go to console. All right, so let's get something huge. All right, let's get 10, 2, 3, 4, 5, 6, 7, 8, 9. Let's do this. Oh, wow. That's pretty fast. All right, let's do 60 and 120. Oh, wow. I have confidence. Submit. Ugh. Holy shit. Wrong answer because I didn't return anything. They did not hit? What? Holy shit. All right, this is interesting. This is interesting. Well, can you blame it? Wow, they did not hit. Yeah, I'm actually curious. So they come out and then do not hit. What? What is this? All right, I want to print L and R. $5.35. Left is 5.30. For sure, left. So left is plus, which means 534, right? 534 is the last one we handled. Oh, we probably want to print more. Let's just print left LCM. Okay. So 535. Well, 534 is the last one we tried. So 534, I say I'm gonna go with A. All right. So 534 times A. What's A? Is 8. Right again. So A is 256. B is 389. N is 885. Okay. So the current would try is 534 times A, 256. Okay, that gives us a value. We call it 136704, right? And MB is this value divided by B. B is 389. So that give us 3. So hold on. So MA, currently MA is equal to 534. So MB now, we calculate is 351. MD is 136704 divided by LCM. LCM is 99584. So divide 99584. That's 1. Alright, so in total we have 534 plus 351 minus 1. 884. So this value, so this is 884. Okay, so this one corresponds to 884. Okay, we say it's too small, so we try it again. Right, so now MB is going to equal to 534. Right, so if MB is 534 times B 389, right, this one gives us 207726. So that's definitely too big, but we're going to still try. And it's 811 for the MA. And 99584 2 on MD. So this will be 534 plus 811 minus 2. So this one gives 1,343. So that's too big, right? That's too big. So that's too big. So we say, okay, left will be plus 1. And then boom, we got out. Wow. I think it means, I mean, it does make sense, right? So we get a certain value, and to take the small side is too small. The big side is too big. So the small needs to increment, right? Small needs to increment. I mean, in this case, I think I know. So basically, this one tells us the high bound, right? This tells us the higher bound. So the remaining will be just trying from this one go up. And I'm going to try to find the next one that can. Okay. So basically, we're going to just try the next one. It's not really the next one, but close. So we do this, right? And of course, if we do this, right, we're not minus 1. I'll stay here. But this one was still, right? So we'll come out. We have the left is 535 when we come out. So 535 would come out. So L plus and then come out. So we have not tested 535. So I think it's 535, right? No, it's not 535. 535 if we times 256. That's still too small. It's slightly small. Oh, 5 actually too big. 136960. Oh, come on. Think, man. Think. But we jump out because 534 is too big. No, 530. MA is 534, right? And the blah blah is no good. And then 534 too small. And then we do this as MB, and MB is too big, right? When MB is too big, MB is, this one is too big. Why do we do left equals? Yeah, that's the issue. Hold on. 884, yeah, this one's too small, right? If it's too big, then we already just shut it down. Now this one is too small, right? So 534 is too small for this one. 534 is too small for this one. Therefore, we go here. And we go here, 534 is too big for this one, right? It's too big for this one. What if it's too small for this one, then we're going to do this. But it's too big. That's the issue. If it's too big, I should not do this, right? I should not do this. If it's too big for this, then if it's too big for this, then what do we do? Well, it's too small for this. It's too big for this. Then it should be starting from 535. We're going to go down, right? Yeah, it's too, hold on. Let me think again. It's too small, right? So this value is too small. We need a value bigger than MA times A. Right? That's what we want. We want a value bigger than MA times A, but a value smaller than MB times B. So this one does give us the range, right? The range. But we know it has to be larger, right? It has to be larger than MA times A, but the value cannot be larger because this one comes out, right? So what we do is we need to decrease from this value, right? From this value, decrease. What are you saying? What I'm saying is I'm going to add another condition. So if this one is smaller, so both of them, so that means it's too small. Then we're going to do big, right? And we're going to continue. And the last one is if it's too small. So it's too big in here, too small. So this one is L plus R. Let's just do mid. It'll be easier to handle, right? So mid equals this, and this equals mid. All of this is mid. At least these two is mid, right? And this one is going to be mid, and these two will both be mid. All right. So now this one is mid is too small for A, but too big for B, right? So what do? We can decrease mid and check for B only, because we cannot increase. Because all of this, we already guaranteed that if we increase mid, it's going to be too big, right? It's going to be too big. So we can decrease mid and check for B only. So in this sense, we just say well, we basically broke out, right? So we broke out because it's going to be and it'll be too small, and oh, that's going to be mid, right? It's going to be mid plus 1, right? You say if it's too small. Yeah, but now it's too big, right? Now it's too big. So now it's too big. Then we simply break, right? So when we break, we can obtain the mid. Wait, why is mid is 443? Hold on. What's 443 times 389? That is still too big. But 443 times 256, that's too small. So what does this mean? This means what's L and R? Wait, I have not converged yet. I have not converged yet. This is not right. Wait, don't break. Oh. So what does this find? What does this find? This will find the find something, right? If it's too big here, then we need to go. So it's too small, right? Too small. So we find the lower bound. We find the lower bound on. Find the lower bound on A. Okay. So that means the value cannot be smaller than what we have for A. Okay. Okay, yeah, okay. You know what? Yep. We do this, and then we come out. When we come out, we know that when we come out, L is now L minus 1 is too small for A, but L is too big for A. Thus, L is too big for both A and B. Thus, the solution must be the solution must come from B, right? The solution must come from B, and with the higher bound being L times B. All right, so we just go from this, we go down. Okay, which means we're just gonna go with L, right? When I say while true, all right? We know L is too big, so we're gonna start from. Okay, res, right? Not res. When you say L minus equal 1, all right? Now while true, MB will equal to L. MB always L. MA equals MB. Oh my god. Divided by A. Alright, and MD equals L times B. No, times B divided by, and I don't need this, right? Oh, we can just say this and MB. And yeah, MB divided by LCM. And we say if MA plus MB minus MD is equal to N, then we break. Now the return MB times B mod, right? Otherwise, MB minus equal 1. So we just search. Ooh, that is not right. What are you saying? LCM. Oh, MB will equal to L minus 1. There we go. There we go. That is the trick. And of course, everybody else, we don't have to use it. This is the only thing that we need to use. Yeah, it must come from B. Or it must from B with a higher bound being L times B. So we start from this, right? Because we cannot be, so we already find the lower bound for A, right? Because all this search, all this search is to see where it fits A, right? So this is the search where it fits A. And of course, along the search, we also try to see if B fits. Well, in that case, do we even need to do this? Like, isn't this can be combined with this? So we're searching for A, right? We're searching for what is the yeah, I think we don't need this. This else, this, right? So this is trying to find the position where if it's larger, if it's smaller, so it's relative to A where it has to be. So this one, right? This one is search for the value hold on. Is this gonna work? Yeah, it's gonna work too. But this can be search for the value that is smaller. Now that is because the last one is this is too small. All right. Search for L, right? Such that L minus 1 is too small, but L too large for A. Yes, that is correct. So when it comes out, now if along the search we obtain the correct value, then good for us. All right. Otherwise, we know. Otherwise, we know that we know we know the value, right? Oh, no, we know the value must be bigger than L minus 1 times A. Must be bigger than this. And only achievable from only achievable from B. Thus, we can search from L minus 1 times B down. So this is search, right, from L minus 1 times B down. Okay. So with this, I'm going to try it again. Hopefully this time it works. All right, try it. Uh-oh. Uh-oh. I got an issue. Well, try it. That's fine. That's how we handle this type of thing. We just try it. Just another situation that I did not consider. Oh, I don't even know the value. I'll just call it 1. All right, let's see. This one will definitely go out. So we're going to print LCM as usual. And run it. Oh, okay, I'll do now run. I need to comment out this. Okay. So, oh, holy moly. That's the, all right, what's the answer to this one? I need observation on this thing. I think we're getting close. Just a few edge cases. If we take a look at this, I think we can see getting close. Now, it is tough. We're getting very close. $48 out of 30, out of 70. All right, so the answer, oh my goodness, that's a huge value. Doesn't matter. I probably need Python to do this. I don't think my calculator can handle this. All right, so we have this, right? What do we want to know? We want to know L times LCM, not LCM, L times A. Right, when it come out as L times A, and L minus 1 times A. Oh, we need a mod. I'm starting to suspect maybe I should not delete the other code. Uh, 26128.3. Yeah, that is too small. Yeah, I suspect maybe we should not delete the other code. Alright, can we get this one back? Yeah, we should not. I realized because as we're searching for this, it might work for the other one. Well, but if it works for the other one, why would this one not be right? Right? We are in the... Well, I never said that it's... Want to try? Or we can print this. All right. Come on. Okay. We're looking for the n. Is this value? Holy moly! The starting is so big. Oh, the difference between the two is huge. So I timed out. Oh, it shouldn't be another binary search here. Yeah, there should be another binary search here. How? Well, we know the lower bound. No, it shouldn't be the lower bound. No, this is actually the higher bound, right? The L, they come out. That's the higher bound, so it will not be larger than this. Yeah, there should be another another binary search. Okay, so we say left, right again. Well, left will be, I don't have a lower bound for this, right? Because I never checked for this. So 1, 2, I know the higher bound is going to be L minus 1, right? That's the higher bound. Well, actually, we can just say L to be on the safe side. And we're going to copy and paste exactly the same thing. Exactly the same thing. But we're going to change. This is going to be MB. It's going to be MA. So MB is this, which I just realized is not necessary because I can simply do this. MA is this. Yeah, now I'll go back to MA, right? And then we can just say MB is this. And MA is going to be MB times MB times A. No, times B divided by A is going to be times B divided by this. And then we do this equals this. We're going to say MB times B mod. Right? Otherwise, we say if this is larger, then R is mid, elsewise L. Let's try this. Oh, there's no mid. MA. MA. Right? And this is going to be both in the MB. There we go. 2 rounds. But L too large for A. Right? So that's the first. And now, once this breaks out, we can say oh, that doesn't really matter. We can even do binary search from the start. We just do 2 rounds of binary search, see which one gives us the result. Now we know that L is L from the previous binary search is the upper bound. It cannot be larger than L. It is the upper bound. So we will search for B Yep. Now it looks pretty straightforward. It's 2 rounds of binary search. I do need this, we need this, and then 1 round and 2 round binary search. You also localize it. Alright, come on. This one you shall give me. This one you shall give me. Let's go. Booyah! We got it. A bit confused at the beginning, but eventually we are able to solve this. Hey, it's a hard question. It's not. How should I say? It is. I mean, so since if n is small, right, this problem can be solved by merging two sorted list in ON. However, n is too big for ON, thus intuitively we need to use a solution of O log n, right? This means our target solution is most likely binary search. To perform binary search, we can binary search for the multiplier, right? For the multiplier, the smallest, the higher bound of multiplier at the beginning must be 2 times n. Once we obtain, we will search based on the smaller of A and B. Okay, let's assume A is smaller than B. Then we will search based on A, right? Based on A first. We know mid is the midth, right, value in the sorted list of multiples, in the multiples of A, and mid times A divided by B is the this is the multiple of A is the this value in the multiples of B, and mid times A divided by LCM is the this, right, LCM value in the multiples value and duplicate values for A and B. Thus, the actual count is mid plus this minus this. If this count is larger than n, we shrink on R, otherwise we shrink, we increase, we expand on L. Well, if we find the solution during this binary search, then that's good. Otherwise, we know that the solution must not be a multiple of A. Thus, we perform the same binary search on B and will be guaranteed to find the solution. So that's going to be O log n, all right, and we ran in 32, all right, milliseconds, and a 72% ranking. Pretty good. I think the solution is very straightforward. Oh, we have a math solution. Binary search. I think this is the one we do. Oh, that's different. I only do one round of binary search. Okay, that's actually different. So I need to read this. But before reading this, I'll probably need to go for A and B. What's A and what's B? All right. The pattern of magical numbers repeats. That will be the least common multiple of A and B. If x smaller or equal to L is magical, then x plus L is magical. There's LCM, right? So if some value smaller than, then plus LCM is magical. That is true, right? That is true. Yeah. There are L divided A plus L divided B minus 1 magical numbers less than or equal to L. That's true. And 1 is a duplicate. We can count by m at a time. Now suppose n equals m times q plus r. The first L times q numbers containing, and what the next number is L times q. We want to find r more magical ones. Oh, that is true. There are m magical numbers, so we just keep going m. And then if n equals this, we just need to search, right? First L times, wait, hold on. M is the number, so we go the first L times Q numbers containing M times Q magical numbers. That's true. This is the bound, right? The bound is L times Q because L is the LCM, right? So we check every M value, so M value ending in L, right? So this is the lower bound, and now we just need to find basically within this R, right? Just within this R to find which one it is. If R is yes, we return. Otherwise, we yeah, from 0 we finish. Oh, nice, nice, oof, nice, good. Our binary search. I'm going to read binary search first, later, but I want to try this. Let's try the good solution. Oh, that solution is good. All right, so this is the math-based solution. Math-based solution from the official solution. But the idea is that any value, right? If a value x, if a value x smaller than LCM is a magical number, then x plus LCM must also be a magical number, right? Thus, once we have found all x smaller than LCM, or magical number, right? Magical number smaller than LC, smaller or equal to LCM, we can all other magical numbers must be numbers. X must be x plus k q times LCM. Thus, our search, thus we can first perform what? So we know, okay, let's do this. The number of magical numbers smaller or equal to LCM is LCM divided by A plus LCM divided by B minus 1. We can call this L. Alright. Thus, we can shrink our search range down to Q R equals div mod L. No, it's N divided by L. right? Where LCM times Q is the lower bound of the value, right? And the actual value will be found within R, within R iterations. Right. So I'm going to do LCM. Right, and so QR equals div mod. I'm going to do L equals to LCM divided by A plus LCM divided by B. That's 1. Right, and this is going to be N divided by L. Another quotient, and we know that. So then what? Then is just merging the two, right? And just merging the two. And basically counting as well. So, so LCM times Q is a lower bound, right? Because I have remaining. So when I say res is equal to LCM times Q, actually do mod on this. Mod, right? Okay, let's do mod. Right, so res is this, and we just say for this in range R, so it will not be more than R. And every time I'll count for this is going to be L times Q, right? That's the current count. And then we say, what do we say? Well, depends on, we need a, so start from LCM times Q, right? LCM times Q. And we need two values. We need two values. So we need to see head A and head B both is equal to this. Right? And then, okay, and what? How can you say while count is smaller than n, right? And then we're gonna just count. How do we count? We say if head A plus A is smaller or equal to head B plus B, right? Then if head A plus, or just go next one, then head A plus equal to A, right? Head A plus equal to A, else head B plus equal to B. So we pick the smaller of the two. So anyways, we have A and 2, right? So we're gonna add, right? We're gonna add one, we're gonna increment A, the other increment B. Right, hold on. That's not right. It should be the current smallest between the two. That one's the next one, right? So should be the new head, right? Should be the new head. They start with the same, and then we're gonna add one. So always we're gonna add. So head A always add. Okay, so head A. Okay, head B equals this. Head A equals head B plus A. And this is the count, right? We'll do this, and we say count is actually this plus one because I already add one, right? And we say if head A is smaller or equal to head B, right? Then head A do this, else head B plus equal. Every time we do this, count plus equal 1. Now in this case, we can assign everybody to the same value, right? Yeah. And then once you're done, so somebody will have increment, right? And then we add something. And okay, hold on. So we have the current, the smaller side, right? We have the smaller side, and then we add something. So this one becomes bigger. All right. So the current count. The count is pointing to the bigger value, right? The count always going to point to the bigger value. And then the count is pointing to the bigger value. So when we start, one value is smaller than the other. So the smaller value we're gonna plus. So we add a new one, right? The start is the same. So we add a new one. So we count increment, and then we compare the two. And once we compare the two, so one will be larger, the other will be smaller. So the smaller will plus as well. So we count, point to the bigger value. And then we will add another one. I don't know about that. If head A is small, come on, just merging the two things. Yeah, we shall return the smaller of the two, right? And once increment on one side, right? We just return the smaller of the two. Every time I will increment. Well, what if I increment? Well, and this one I'm assuming A is smaller than B, so I do need to do this one too to make this easier to handle. All right, so A is smaller than B, therefore we always add A, right? We add A, but shouldn't we not count? Well, because A is smaller, so if we add A, that's add a small, so we can always count, right? Oh. Hold on. What are we doing here, right? So we start by adding, right? And then we'll add this. Then we will add again. And every time we add, we are increasing the count. But if we add B, if B is huge, then that should not count. Shouldn't we just take the smaller of the two? I'm gonna take this small. Oh, I cannot do this. Come on, man. This is so simple. It's just merging two sorted lists, and they start from the same value. They start at the same value, all right? And then we just add. Now we take smaller of the two. Okay, so we add. Shouldn't we like add the larger, and then we start? Yeah, I think that's the one. We shall add the larger one because this we start from the same, right? We start they're the same. So we add the larger one, and then we go into the loop, right? And then we say if head A is smaller than this, then head A plus. Then we will increment the count. Then do it again. If it's still smaller, we head A will add again. Then we'll do the count. Now head B is smaller, right? And head B is smaller. Then so every time head B is smaller, we do the count and then increment B. And next one, head A is smaller. Now we increment until we come out. So we add this. We add this because it's too small, so we add this. But every time we add, so we increment at different times. So what are you saying? I'm saying is head B, I will add right now and then count. Head A, and then we're going to count here, right? Else we're going to count. Then add head B. And then we're going to return. So what's the difference? The starting will be smaller, so I'll add a count. Go back, still smaller, we'll add a count. Go back, if head B is smaller, then we will add this and then count. But the count is count the previous one, right? Count the previous one. So when we break out, right? So the count is count the previous one, right? So when we break out, it's going to be the smaller of the two. So we're going to return the min, head A and head B. It's a mod. Why don't we mod here? can mod here. It's fine. With a mod, right? And this is going to equal to head B plus mod. In this case, it's the same, right? We just need to do the count at the end. Let's try it. I'm not confident, but it does pass. Okay. Yeah, I think this is the key step is here. Yeah, I was a bit confused when I was going through this. All right, try this one. Wrong answer. Yeah, understanding of this is still lacking. Expected this. Oh. Count is L times Q. This is right. Ahead shall be this times Q. Yeah. And we mod. I don't know, man. Head A, head B, right? I'm just gonna keep counting. All right. How about we and print head A and head B. Okay. They're small, right? They're close, but they're small. And what is the count? Count is this. Oh. You need like almost like 10,000, a couple thousand. Which is fine, right? and we always pick, so B is bigger, right? So now this one is smaller than this, so we just head A. Okay, we do A. And then if A is larger, then we'll increment B. And every time we increment, we will record a count. What's the next one? 887859796 minus 88779842. We're looking for about this much, 61,000, right? So if we say 61,000 times 29911, that is a gigantic value. 2, 3, 4, 5, 6, 7, 8, 9, 10 to 10 value. Don't know, man. So I'm modding these two, right? I'm modding these two. Oh, I'm modding these two. Are you telling me we should not mod? Yeah, because mod we cannot compare the mod. Okay. Well, that makes sense, right? We cannot compare the mod. And we do the mod at the end. Right? Do the mod at the end. But isn't this gonna like overflow and stuff? I mean, I'm not gonna overflow on Python, but if we don't mod along the way, it's gonna get slow. How do you handle that? They did not handle it. Okay. Alright. That's fine. And we do return the mean. Yeah. Yeah. We cannot compare after mod. That is not wise. That's fine. Double check one more time all the previous solutions. Yep, works. All right, this one shall be right. There we go. All right, last one. All right, binary search. Let fx be the number of matching numbers less than or equal to x. Yeah, I know this. The answer must be between 0 and n times minimum a and b. Suppose a is larger than b. Divided by a plus divided by b minus must be larger equal to this. A is larger equal to GC. L is the least common multiplier. The high as n times, well, we directly do the value itself. So high is going to be n times this. And then this is the mid. And we say mid. Oh, we directly do it. Okay, we find the high value. We're already doing it. We're already doing it. And we say if it's n over the term, if it's smaller than n, and we just we can directly do it. I don't know why I did not do that, because I was binary searching on the multiplier, but we can binary search directly on the result. Binary search directly on the result from the official. Okay, so we have, of course, we need all of this. Right, this is our start, and we're gonna go left and right. Left is 1, right, I'm gonna do a times n. Right, that's the maximum. That's the higher bound, right? And we just say while L is smaller than R, mid equals L plus R divided by 2, right? And once we got the mid, then we can say, we're going to count how many. If mid divided by A plus mid divided by B minus mid divided by LCM, right? We say if it's larger than n, right? If it's larger, then what? If it's larger than n, which means this value is too big, so our R gets smaller, so R does not change, so R equals mid, else L plus equal 1. Now I'm going to turn L mod mod. Right? I don't know. Oops. Oopsie daisy. That's not right. If it's too big, the right needs to be smaller. Ah, which one? Which one failed? Well, let's check this. Ew. That's bad. Huh. This should be right. Okay, so we get a value, and this value is too big, and R equal to, hold on, let's print out LR mid. Look at this. Look at this. L is 12, R is 14, right? And it's 13. 13 is too big. No, it says 13 is too small. How is 13 too small? Thirteen divided by 2, that's 6. Divided by 3, that's 4. All right, that gives us 10. Hold on. 13, right, divided by 2, that's 6. And 13 divided by 3, that is 4. And minus 13 divided by 6, that's 2. That's 10 minus 2, that's 8. That is 8. Then L plus equal 1. L does plus equal 1. And that's 13, so L plus equal 1. That's why it came out as 14. This is actually, we're searching for the larger one, so we should not do that, right? We need to shrink. We want to shrink. Because we want to find the smallest. Like if it's 13, it's good, so we need to go down to 12. So shouldn't we, what if we change to this? If it's equal to n, then it will remain the same. But in this case, if it remain the same, if it's larger or equal to, we always reduce on r. Or if it's equal, we stay at r. So now in this case, 13, r doesn't change. Now we want it to go down, right? We want this to go down. Okay, I can do this. And we change this to equal to. Because if we don't do equal to, that will be too small. All right? So if we do equal to, that will pass. Because we are shrinking on the right side. Right? We're shrinking on both on the right and the left. So once we equal, when L and R are equal, so we keep shrinking on the high side. So there will be, and we will shrink, right? And then and L equal to R, right? At the last one, L equal to R, and whatever the case, either R shrink down. That means when R shrink down, it's too small. I think this one shall work. Ew, that's ugly. You're not supposed to print anything, man. Nope. What happened? It stayed the same? How? Why would it not work? They all pass. This one passed. This one had problem. What was the problem? We can check. No, it is changing, right? It's left, right, and a mid. Holy guacamole, they're just left and right. The difference is too big. Oh, left. Mid plus 1. God. Oh, mid plus 1. Well, in that case, if mid plus 1, can we change it as well? Yeah, I think I got it wrong earlier. I don't know. No, we cannot, because we want to shrink. Alright, so we have to shrink. And if we want to shrink, then this has to be minus 1. In that case, this has to be equal to, right? And then we'll keep shrink. Once we're done, we'll come out either the right shrink too much or left need to plus O. We're guaranteed that result shall be, yeah, this one I think it should be right. Yep. So it's a direct, right? Let's say it's a direct search. Should have thought about this, a direct binary search. I was already doing binary search. That was actually very close. Now, in this case, I don't even need this, right? This line is not necessary. Oh, this is fast. Yeah, this is not necessary. Oh, wait, it is. It is, because we need to find a higher bound. But it's fine, right? With this binary search, it's not going to cost too much time. So we don't need this. We just arbitrarily say it's going to be A times N. It will work, no matter what. But this one's faster. logN. Well, that's a log. I mean, we can do, say, min AB. So it's the N times min AB. 20, 28. Wait a second. All right. Well, that's a good one. It's a good question. I like it. Okay, I'll be done by now. I'll see you guys tomorrow. Adios.